In this video, we're going to discuss the greenhouse effect and planetary atmospheres and get a little tour of the solar system with the atmospheres of our planets. So one thing that astronomers are interested in is the expected temperature on the surface of a planet. And this temperature depends on an energy balance. We have energy absorbed from the sun. Of course, if we're closer to the sun, then the sun's going to be brighter and more light and more intense. But we also have to consider the albedo, the percent of the light that the planet reflects. If the atmosphere is very cloudy, then it can reflect more. On the outgoing side, as the planet has a temperature, it emits energy, primarily in the infrared wavelengths for the temperature of the planet, at least for the terrestrial planets. More energy is emitted if the temperature is higher. If you remember the study of the black bodies and the continuous radiation there, as the temperature goes up, we have more energy emitted at every wavelength. So more energy goes out if the temperature is higher. So the planet establishes a balance. The amount of energy absorbed is equal to the amount of energy emitted at a certain temperature. If the planet is absorbing a greater amount of energy from the sun, the temperature will have to go up such that the planet radiates off that equivalent amount of energy. If the energy would go down for some reason, the planet will cool off, sending out energy to space until again a balance is reached. So energy absorbed equals energy emitted by the planet. So we have this balance in place for the planets in the solar system. They've been orbiting the sun for a long time, and the balance is set up, but it can be disturbed if something comes into play that increases the amount of energy absorbed or restricts the amount of energy leaving the planet. If that's the case, then the temperature of the planet will go up if the energy is blocked from leaving the planet. But the basic relationship, the amount of energy absorbed is equal to the energy emitted. We can modify this a little bit in that this energy emitted will increase. The temperature goes up, the energy emitted will increase. So we'll get to more of the details with the greenhouse effect here. There are certain molecules that preferentially absorb infrared light. Certain types of gases will absorb infrared light. The clouds have water molecules that absorb infrared light, and scientists are concerned about the abundance of these molecules and the greenhouse effect for the Earth's atmosphere. They play a role in the other planets as well. So the planet's temperature will go up if there is this greenhouse effect in place. The reason for that is in order to get the energy going out through this barrier of these molecules, more energy has to leave the surface. If some molecules are trapping the energy and sending it back down to the surface, a certain fraction, certain percentage, the planet's surface has to emit more energy such that the amount that eventually breaks through, goes out to space, is equal to the energy absorbed. On the Earth, well, the scientists calculate that the greenhouse effect that's already in play has a benefit to the Earth of raising our temperature about 60 degrees Fahrenheit. So our global temperature, I think, is around 50 degrees Fahrenheit. If we did not have an atmosphere, no greenhouse effect, our average global temperature would be minus 10 degrees Fahrenheit. This greenhouse effect for atmospheres is somewhat different than the greenhouse effect for greenhouses. A greenhouse has glass that traps in the warm air. Our atmosphere has molecules that absorb infrared and somewhat trap the energy, sending it back down to the Earth. But gases, of course, have no top surface, no cap. What's a cap for the atmosphere are the molecules that absorb infrared light. So here's a little bit of a complicated diagram. I'll let you peruse this a little bit before I comment on it. So we have sunlight sending energy towards the Earth. Earth has an albedo. Some sunlight reflects from clouds or from ice and snow on the surface. So we have sunlight, some making it through and being absorbed on the surface of the Earth to warm up that surface. The surface responds by emitting light in the infrared, trying to send that back out into space. Gases in our atmosphere can absorb that infrared radiation, and this primarily happens near the surface of the Earth, not at the very highest point in the atmosphere. But they trap some infrared, send it back to the Earth. That warms up the surface some more infrared is sent out, and eventually we reach a temperature on the surface where the amount of energy able to get out equals the amount of energy absorbed. So energy absorbed equals the amount of energy eventually leaving. The greenhouse effect part of this is that because of the gases that absorb infrared light, the Earth's temperature has to be warmer to get that amount of energy out of the atmosphere. A certain fraction of the energy is absorbed by the greenhouse gases and sent back to Earth. The response to the Earth of that is to increase its temperature such that the amount of infrared that gets out into space does match the energy absorbed from the sun. Another diagram of this, I'll let you peruse this one also just a little bit. Again, showing energy balance, the incoming solar radiation eventually warming up our land and atmosphere and oceans. And we get energy emitted back out into space. And that energy emitted equals the energy absorbed by the Earth. So what are the greenhouse gases? The primary greenhouse gases: carbon dioxide, methane, nitrous oxide, fluorocarbons, and water vapors plays a role in here as well. You don't need to memorize these numbers for my class of the concentrations. Methane here, if I convert this to parts per million, it would be about 1.7 or 1.8 parts per million. So carbon dioxide is much more abundant. Again, nitrous oxide, not that abundant either. This pollutant from burning fossil fuels. So some of the sources we have for carbon dioxide: plants, when they decay. We have fires that release carbon dioxide, volcanoes. There's water around our planet and the Earth that has carbon dioxide in it. As the oceans warm up, they can release that carbon dioxide. Man's contribution to the production of carbon dioxide: fossil fuel burning, having less plants on our land, more buildings. Those plants remove carbon dioxide, so if we destroy our vegetation and forests, we lose that ability to remove carbon dioxide from our atmosphere. Methane with animals, also produced with fossil fuels, livestock that's raised in great numbers. Nitrous oxide, a little more of a minor effect here. Styrofoam production, and the fluorocarbons and such. So impact on greenhouse effect: carbon dioxide is the winner of having the most impact. And you can see methane is important, even though it's a lower percentage of our atmosphere, by a factor of about 200 compared to carbon dioxide. It plays a significant role in the greenhouse effect in absorbing infrared light. But carbon dioxide is the most important as far as creating this greenhouse effect, the warming of the surface of the Earth by trapping outgoing infrared radiation. So a little bit of talk about the atmospheres here. We've mentioned these before as we've discussed the planets in general, but Mars has a very thin atmosphere, a little bit further from the sun than the Earth. The average temperature, minus 50 degrees Celsius. 0 degrees Celsius is where water freezes. So very roughly, 70 degrees below zero on the Fahrenheit scale. Earth's temperature 15 degrees Celsius, that's around 50 degrees Fahrenheit. And Venus, a very thick atmosphere, and average temperature 420 degrees Celsius. If I remember correctly, it's about 800 degrees Fahrenheit, with this carbon dioxide creating a runaway greenhouse effect on Venus. We'll talk a little bit more about that when we talk about Venus in particular in a future chapter. But carbon dioxide on Venus effective for greenhouse effect because it's a thick atmosphere. Carbon dioxide on Mars not effective in greenhouse effect because it's a very thin atmosphere. Scientists have done studies of the temperature of the Earth and the carbon dioxide in the atmosphere for 400,000 years. Has there been technology for people to sample the air 100,000 years ago, 300,000 years ago? No, but ice cores can be taken where we have permanent ice, drill down into that ice. There are bubbles in it that have the atmosphere trapped in there that was present when the ice formed. And studies can be done, the effects of temperature can be analyzed, and there is a correlation that when the carbon dioxide concentration is higher, the temperature of the Earth is higher. That's just what this graph shows. The carbon dioxide and the Earth's temperature are in sync. Now, this does not prove that carbon dioxide makes the Earth's temperature higher, but it shows there is a correlation, something that's worth studying, the amount of carbon dioxide and the temperature of the Earth. What's happening more recently? Again, from studies of ices, we can get a measurement of the temperature that's been occurring, and what we see dramatically in the last 100 years is that the temperature is rising. This is the northern hemisphere. So some people call this sort of curve like a hockey stick. We've got the handle of the hockey stick here. And there's been a big change with the Industrial Revolution, the burning of fossil fuels, coal, oil, and such. We're getting a big increase in the amount of our temperature. And big, half a degree Celsius, so roughly 1 degree Fahrenheit. But it's a substantial change compared to the past history, 800 years or so of the Earth. We are seeing a significant change. We're also seeing a change in the amount of carbon dioxide in our atmosphere. There's been a recording station on a dormant volcano in the Hawaiian Islands, Mauna Loa, that's been reading the concentration of carbon dioxide. And going back into the 1950s here, you can see the value starts out about 315 parts per million, and has been tracking upward through the early 2000s to up over 380 parts per million. This graph goes up and down each year. That most of the landmass of the Earth is in the northern hemisphere. During the summertime, we have plant growth that removes carbon dioxide from the atmosphere. So those are the low valleys. The peaks are in the winter in the northern hemisphere when the plant activity is reduced and the carbon dioxide goes back up. But it is a dramatic increase in the amount of carbon dioxide, or actual measurement, not just using ice core samples or something, but actual happening here. Carbon dioxide in our atmosphere is increasing. So the CO2 concentration and a graph of temperature, global temperature, where there's sort of an arbitrary midpoint here, where the blue and the red arrows or bar graph is drawn from. But this would be the temperature, and just indicating cooler temperatures in the early 1900s, a trend of warmer temperatures in the late 1900s for our global temperature. And a big part of this carbon dioxide increase is from our use of fossil fuels for energy, coal, natural gas, and oil. If you look at those, that's a big slice of the pie, releasing carbon dioxide. Also, biomass releases carbon dioxide. energy from nuclear power, hydroelectric power, a little bit of solar power, wind, and very limited input into our energy system. The cheaper fuel, easier to use right now, is the fossil fuels. So that's our motivation for continuing to burn things. Cheaper fuel and easier to use. There is a problem of if we warm up too much, there's methane trapped in permafrost and carbon dioxide trapped where in the Arctic, where it warms up and gets released, or we can obtain some of these molecules from the oceans. We could reach a point where there's a great release of infrared absorbers into our atmosphere, and we could reach a place where the temperature increase accelerates. Some of this has some debatable issues to it, but many scientists are concerned that we may reach a point where we can't pull back. There's too much natural forces in play that's releasing greenhouse gases. So that's where I'll stop here. Next video will have planet atmospheres.